friends, welcome, welcome. For those of you who can see me through the open door, welcome to Moonshot Museum. We're really glad you're here. Moonshot Museum has been open for all of 3.5 weeks, so you are amongst the first people to see it, the first people to be in it. You're also getting a really special perspective tonight through the clean room windows into the clean room where Astrobotic is building the Peregrine lunar lander. We are really glad you're here because this is why we're here. We are here at Moonshot Museum to provide a window into the 21st century space industry, to bring you up close to that work, and to partner with incredible partners like the Community College of Allegheny County and showcase the work that you're doing around space exploration. So thank you to CCAC, thank you to Justin, thank you to Justine, Francis, Carrie, our incredible judges tonight. We're glad you're here. A couple of housekeeping items before we get rolling. If you haven't found them already, restrooms are right around the corner here, so pretend you're going to exit the museum and then take a hard right before you leave. You'll find the restrooms there. We're also obviously a pretty unique space here, right? We're not swimming in seats, we're not swimming in elbow room, and this space is really, think of this space more as a TV studio tonight than an auditorium. So as different groups of students come up, if you are here to see your students present, your friends present, go ahead and step in at that point and grab a seat, and when they're done, step back out because there will be some more people who want to come in after you. So it's going to be a little bit of an ebb and flow, more casual tonight, but we're really excited to have you here. We appreciate your flexibility, and again, welcome to Moonshot Museum. The work of space is real in Western Pennsylvania. The opportunity to work in space and what that offers is very real here in Pittsburgh and Western Pennsylvania. But I have some friends coming up here who are going to talk much more about that. I am very pleased to introduce the esteemed Dr. Bullock, president of CCAC. Thank you for being here.
Thank you, Mr. Moore, for the warm welcome. It is a pleasure to be with all of you at the Moonshot Museum this evening as we welcome the 12 teams from the Community College of Allegheny County who will be competing for the opportunity to make their mark on this exciting field of space research. On behalf of the college, I would like to extend my profound gratitude to everyone who has had a hand in making today's event possible, including our wonderful host here at the Moonshot Museum. I also look forward to the many future innovative initiatives and collaborations that will occur between our two institutions. It is also my pleasure to also recognize Dr. Justin Starr for his commitment, creativity, and vision. Additionally, I wish to acknowledge our esteemed CCAC faculty team leaders and expert judges who are so very important on the mission today. I understand that the Community College of Allegheny County is one of 3 two-year institutions in the nation to be invited to participate in the Students' Space Flight Experiment this year. I think that deserves a round of applause and recognition. Dr. Starr and his team secured this exceptional opportunity for the college by proposing that we also include spaceflight experiments devised by CCAC students who are studying outside of the STEM curriculum. His brilliant presentation won us a spot for this opportunity today, which embodies everything that the Community College of Allegheny County stands for. Community colleges represent our future. We are challenged to look beyond the traditional higher education universe and forge new pathways in order to serve the diverse and evolving needs of students and employers. At CCAC, our mission is to ensure that access to an exceptional college education is available to all who seek it and identify our institution as the point of access. One way to do this is through programs like this one today. This partnership and programs that enhance knowledge, inspire curiosity, and develop within our students a lifelong passion for the pursuit of scientific discovery. that will open doors and provide infinite career possibilities. These are opportunities that a solid foundation in the sciences have to offer. And it is for that reason that I have come here today to recognize the passion of scientific discovery that is present within our amazing students. You are true explorers, and no matter which experiment is selected tonight, I congratulate each of you. You deserve it, and tonight is the time for you to shine. How many people can say that they worked on an experiment that potentially be conducted on the International Space Station? I ask the question again. How many community college students can say that they worked on an experiment that will go on the International Space Station? That alone is going to look great on your resume. So I ask the entire team to join me in recognizing all of the students that are participating tonight to show our gratitude and appreciation for your innovation, your desire, and your commitment to make this one of the days of your history. Please join me and give them a round of applause. And finally, I extend good luck to all of you, and thank you for inviting me to participate in this leg of your grand adventure. I will now turn the podium over to Justin Kosnica, board chair and founder of the Keystone Space Collaborative and one of our judges here today. Justin.
Thanks. Good evening. Welcome. And thank you to the Moonshot Museum for creating such a wonderful venue for such a wonderful event. Wow. Congratulations, CCAC, for this amazing program. We are so proud and thrilled to have this hosted here, to have all of you here part of this student spaceflight experiment program. My name is Justine Kosnica. I'm the board chair and one of the co-founders of the Keystone Space Collaborative. We are one of the silver linings of the global pandemic. We were born right before we all went home as a team of space industry professionals who saw a real opportunity in the tri-state region, Pennsylvania, Ohio, and West Virginia, to build an aerospace space industry cluster. We saw what was happening behind you at Astrobotic. They were anchoring an actual lunar services company here in Pittsburgh, Pennsylvania. We knew about the history of Pittsburgh and its participation in the Apollo program back in the 60s and then 70s and throughout. And then we have seen the tremendous resources and assets of the higher education community here, and then the non-traditional higher education community like the community colleges, focusing on tremendous research and development activities, the innovation spirit and entrepreneurial spirit that this region fosters, and then interest in advanced manufacturing, material science, software development, robotics, and other advanced technologies that our region broadly as the tri-state is known for. Building on that, we said, we will build it. We will rebuild a space industry ecosystem here in this tri-state. And what this event tonight represents is the beginning of that. And I'm thrilled that it actually is starting not with a 4-year traditional college, but with a community college and with students that have an opportunity to actually fly to the ISSNL. We're thrilled to have you here today, and for me, this is a real joy. About when we just started the Keystone Space Collaborative, I reached out to Dr. Bullock and had a conversation with him about inviting and engaging with CCAC on space-related matters. That's when he put me in touch with Dr. Justin Starr, and the idea of how do we collaborate together and partner together and network all of these nascent organizations, whether it's Moonshot Museum and Astrobotic, Keystone Space Collaborative, and the work of CCAC to build something that ideally will grow and become a sustainable space innovation opportunity for the region. Since then, our mission here with the Keystone Space Collaborative is to build new companies, build existing companies, grow talent, and then essentially amplify the space work of the region. When you guys work on these projects, when we have these tremendous opportunities in the region, come to us and we will amplify that work to make sure that the rest of the region knows what CCAC is doing, what Moonshot is doing, what Astrobotic is doing. And if you want proof of this, you're not alone. When we first started on this Keystone Space Collaborative journey, we seeded an industry report to take a look at the health of the space industry in the tri-state. What we found was pretty stellar, pardon the pun. But what we found was that across the 3 states, we have over 550 participants that are to date receiving dollars from NASA and DoD for space-relevant work. That's a big number. As a region that that outcompetes Texas, Alabama, Florida, and some of the other well-known space states. What that means is that we have a real opportunity moving forward into the future to take that partnership and to drive dollars to this region, to drive opportunities for real spaceflight experimentation, R&D, and commercialization, and new company creation. We believe that in a 5 to 10 year span, if things go according to plan, our region will be known as a new commercial space region for the country. You are now part of a $1 trillion global market. And it starts with teams like this that are building experiments that will fly, that then can commercialize into new companies, that can get seed and talent and essentially create job opportunities for folks from this region. That's what we believe in. That's what we're committed to at the Keystone Space Collaborative. And I very much am thrilled to have CCAC as a partner and a sponsor of the Keystone Space Collaborative. For those of you students that are here, just a quick shout out as to coming events for us. We had an inaugural conference in April of last year. This year's conference will be in Pittsburgh on the North Shore, and that's going to be June 1st and 2nd of 2023. We will be shortly announcing the beginnings of an actual physical innovation center here in Pittsburgh, so that as you graduate and if you're interested in continuing your exploration of space and space commercial opportunities, we will have opportunities, future challenges for you to participate in. So if you're not on our mailing list, reach out to us, go to keystonespace.org, get on our mailing list, and get involved with all the tremendous programs that are starting to come your way from our organization. I can talk forever on this, but I'm thrilled to be here today, be a judge for this great competition. Again, thank you to everyone who's been involved in this, and to CCAC and to the students. Congratulations. Thank you so much. Most importantly, I need to introduce the man of the hour, Dr. Justin Starr with CCAC.
First order of business is get the slides moving. So, hey, thank you guys so much. This is exciting, and I tend to be a pretty emotive person, but I'm truly overjoyed with this turnout, right? When CCAC applied to be part of the Student Spaceflight Experiments program, we knew it was something unusual, right? It was unusual for a community college to get involved with this, and we didn't know what to expect. And the sky is always the limit, right? We have high expectations for our students because we truly know what they accomplish every day. But to see the Moonshot Museum filled with CCAC students from a variety of programs and all walks of life here is just a tremendous success. So I want to, first and foremost, congratulate our students. We're gonna be clapping a lot, but like these guys, this is not part of their normal college experience. No one is making them come do space presentations like this. The vast majority are interested, and they saw this opportunity and they took it. And the fact that they're here is a real testament to something special we have going on in Western Pennsylvania. So just, I know we're gonna clap a lot for these guys, but we can't clap enough. Thank you to the students who came out tonight to do these presentations. I have to do a couple of thank yous because an event like this doesn't just happen by the will of one person or a couple of people. First and foremost, CCAC partners with the University of Pennsylvania, Ohio State University, and Carnegie Mellon as part of the Mobility 21 University Transportation Collaborative. We need to thank those guys. They provided significant funding to support students doing experiments in transportation and logistics. So sending something into space is really expensive. So anyone who backed CCAC and made it possible for these student teams, we're just very grateful. I also want to thank Dr. Bullock and the support of the CCAC administration administration. This event really requires all of us to work together. You notice the snacks and refreshments outside. The students, you all get a gift bag for participating. We have some wonderful awards for the winners. These things didn't just happen. We truly are lucky to have an administration that supports spaceflight at CCAC. And then finally, Moonshot, right? We're in Moonshot Museum. We're hosting this event somewhere where if y'all get tired of listening to me, you go watch them literally build the thing that's gonna land on the moon next summer, right? The Peregrine lander. I checked with Sam. They're not making them work just for us. It's shipping out Saturday. So they have a tight deadline. The next time you guys see that thing, it's gonna be on the news because it landed on the moon. And here we are doing our event in this space. It's just a super cool experience. So, I just want to set expectations for this because some of our students at CCAC will go on to transfer to four-year schools and they'll literally become rocket scientists. But that's not the path that everyone takes, right? As a two-year institution, some students come to us to become technicians. They come to us for a quick path towards family-sustaining jobs. And we have all of that represented here tonight, right? We have some students who are doing some amazing STEM-based experiments, but some other experiments that don't quite fit into STEM, right? They're a little bit more practical, a little bit more hands-on. Some of them came from students in our apprenticeship programs. Some of them came from students in our skilled trades. Some of them came from students with an interest in things like dyslexia that typically wouldn't be a part of this competition. And part of preparing for this is not public speaking. So just know that our students accomplished a lot. Some of them are going to be a little bit nervous, but tonight's a night to celebrate accomplishments and get excited about space. So please be polite and respectful to everyone who's presenting. I know we're going to be shuffling in and out of the room, and I know y'all excited about space. Just if you're going to have a loud, boisterous conversation, don't have it right here while people are nervous about presenting. Step outside for a minute. Just be respectful to everyone who's going. The last thing I want to note is that, spaceflight today isn't what it was when I was a kid. When I was a kid, I dreamed, want to be an astronaut, too bad, you're too tall, and that was really it. There weren't a lot of careers. Now, when we look at what's going on in Pittsburgh, when our students dream about a career in space, it's not that far-fetched, right? They can achieve it. They can come down to Astrobotic. They can turn in a resume. They could be someone who designs a satellite. They could be a welder. They could be a machinist. They could be an electronics technician, someone who actually builds the satellite itself, or the Peregrine lander right there. The opportunities for our students are real, and these kids are some of the first to take full advantage of it. So before I turn things over to the students, let me just logistically talk about how this is going to work. We have a panel of esteemed space judges who are going to be reviewing everyone's experimental proposal, and I want to thank them for being here and just introduce them. They'll be sitting in the back at the seats that have the papers there, so you can sit anywhere you want, but not there unless you're a judge. We have Justine, who spoke earlier, board chairman and founder of the Keystone Space Collaborative. We have Mike Hennessy, the Director of Learning and Programs at the Moonshot Museum, who not only is going to be a judge, but help coordinate this wonderful event. And then we have two people who probably should be working on the lander at Astrobotic, who are nice enough to step away for a couple minutes to judge student experiments. We have Carrie Quinn, the Principal Mechanical Engineer for Lunar Surface Systems, and Francis Sulai, Lead Propulsion Engineer. So this isn't just academics choosing interesting experiments. These are people really working in space. Each student group is going to give a presentation for about 5 to 10 minutes. Student groups, if you're paying attention, if it's 10:01, we're not going to yank you off the stage, but I'm going to start waving at you in about 10 minutes and 30 seconds. I will come take your time away. So try and wrap up, pay attention. We all want to get home tonight, so just be mindful of time. After each presentation, the judges will ask a few questions, take a couple notes, and we'll move on to the next student group. We have 12 student groups presenting tonight. I don't think they'll all be about 10 minutes, but we're looking at about an hour or an hour and a half for student presentations, and we'll keep things moving. Once the presentation's finished, the judges and I will retire. We'll pick winners tonight, and we'll give every student group a gift for coming, and we'll give the winners a special trophy and talk more about awards. So as soon as you're done, please don't leave. I understand if someone in your group has to leave, you have childcare or a job or something, that's totally fine, but please stick around. We will do the awards, and we'll get everyone out of here before it gets to be too late. So to get things started, I think I'd like to welcome our first group to the stage. So our first group is actually some of my students at West Hills, polymer technician apprentices, who are going to be talking about self-expanding foam in microgravity. So judges, if you wouldn't mind taking a seat and taking some notes. Dan Reese, this is your group. Let's go. ready? Here you go, guys.
Alrighty, hello everybody. First of all, I'd like to thank everyone for taking the time out of their busy schedules to be here tonight. I know we're all super busy. We are a small group of second-year grad students from CCAC West Hills campus. My name is Dan. This is Mike, Ethan, and Jake. We are beyond proud to be working together to create something, that could possibly impact our future. What we would like to submit for our proposal is that we want to create a two-part polyurethane expanding foam in the presence of microgravity and explore not only its viability, but its variety of benefits in the aerospace industry. We intend to prove the cost and space-saving characteristics of this straightforward process by mixing two simple yet customizable compounds that, when done correctly, can yield amazing results. During the conception of this project, we have been lucky enough to gain the partnership of one of the foremost leaders in polymer manufacturing at Covestro Chemical. And we are not only excited about this relationship, but we could not be more happy to be working with a company from right here in the Steel City. We have the utmost confidence that this small, important test could open the door to ways not yet investigated how to solve problems in space. Okay.
So, practical applications, right? These are the applications that we see polyurethane used in here on Earth, and then how some of those applications will apply for use in space. So first up, we have insulation and sealing. These are your easy-to-use application foams. They typically come in a spray gun application or prepackaged canisters ready to shake and use. These foams work well in thin layers as an insulator or hardened coating to an outer surface. And they can also be used to seal small holes and cracks, as well as filling gaps between wall panels. What is interesting about these foams and many others is that they have a wide range of they can be customized for a wide range of uses. For example, you can add a fire retardant to the spray gun, like an additive, and then that would create a sprayable fire retardant foam that can be used. Or you can change the ratio up a little bit. You can create a very dense foam for sealing applications, which has little to no permeability. Next one. And then next up, we have insulated foam boards. These are your rigid material, your building stock. What's interesting is that these can theoretically be manufactured directly in space because they only need 4 key components to be made. You got a 2-part chemical, iso and poly, a large roll of foil to act as an outer shell, and a mold for whatever shape you need for the application. By sending these materials in their raw form instead of their finished bulky product, this saves an enormous amount of space on each launch, leaving room for more equipment or personnel, and in turn that makes each launch more efficient. The structural boards can be used for a variety of applications, of course structural, interior, exterior walls. They make a great sound deadening board. You're in a small room, loud equipment, you want to try and keep things good and economic. And as well, they make a great insulator against the coldness of space, which in space is rather important, I think we can all agree.
So another practical application of our foam is packing foam. I feel like it could be something that's easily overlooked, but it serves its purpose just as much as any other job. So during space travel, there's a lot of force and a lot of different things that happens during it. So especially on launch and then coming back to Earth. So there's all sorts of precious equipment and samples that need protecting on the shuttle. And what's a better way than use the foam to do it? Especially when it comes to samples up in space, where you can make it as you need it and have a customizable fit. With just bringing the raw ingredients to make this foam in some sort of liner, you could have a custom fit packing for anything you need without bringing up bulky materials and wasting room for things you may not even use once you actually make it up there. All right, so cost savings. When it comes to bringing things into space, it's big money. In some cases, for a payload per pound, it could cost anywhere from $1,200 to $10,000 a pound to bring something into space. So that's why we think this is a real cost saver with it being able to expand up to 300 times in size. So with just 2 gallons of material, those 2 gallons only take up 0.26 cubic feet. Well, your finished product is going to be 80 cubic feet by the time you're done. So your mass isn't changing, you're just getting an increased volume once you make your mixture. So I feel like it's very important because you're saving space for other equipment and you can bring more up with you. And it's nice for this because there's so many different uses for it. You could say it's just another thing to save space on your shuttle.
Scientific process. The 2 base materials we'll be using is polyol resin and aromatic isocyanate. Both liquids are stable and can be kept at room temperature. The chemicals will be combined inside the FME tube by opening the clamps and shaking the mix with the aid of an agitator inside the tube. We hope to confirm the raw chemicals will survive the rigors of transit between the Earth and the International Space Station. We also hope to find that the lack of Earth's gravity will increase the expansion volume of the foam, making it even more valuable. We wish to study the cell structure of the foam and document the differences, if any, from how the reaction takes place here on Earth. Our partners at Covestro have offered their services and facilities to analyze and report data from the sample when it returns to Earth.
So, in conclusion, what we would like you to get out of this is the endless versatility of this miracle material. It is customizable, it is adaptable, and it's applicable to almost anything and almost any situation. The space and the cost savings alone make this worth looking into. We believe in this wholeheartedly, and we hope that you guys can see its potential too, and also believe in it with us. The only way this experiment could possibly fail is if we didn't try it. It was Edison that said, after he created the light bulb, he never once failed. He just found thousands of ways that it didn't work. You know, we would be honored if you guys granted us the ability to act on this opportunity and not just watch history fly by us, but contribute to it. Give us the chance to get into the ring. Let us take a swing. You know, give us an opportunity to create our own light bulb and maybe, just maybe, do something incredible. Thank you.
Any questions?
So I have a question. How did you guys come up with this idea?
It was actually, I believe I brought it up to the group. I actually work for Henneke, a polyurethane manufacturing company local to the area. And I have experience with it, and spitballing a few ideas, I was curious to see how some of these chemicals would react in a microgravity environment, or if they would even survive transit. And we played around with the ideas and decided that it was worth moving forward with, and it'd be really interesting to see how this reaction would take place in a microgravity environment, and then the applications it could produce, if it works, are tremendous. Polyurethane is used widely here on Earth in numerous different applications in everyday life, medicine, and industrial applications. So the ability to move that into space is really just a natural next step for this. And we're hoping that if this experiment goes well, it would open the door into further research for that.
Quick question. Have
Yes.
you done any research on how polyurethanes have worked in space environments before?
No. We have done some, we've met with Covestro to discuss a recipe and find a specific foam that would work ideally for these conditions, but we haven't been able to find specific research on polyurethane in space.
So when you say that your hypothesis is that in a zero gravity or microgravity environment, it'll actually expand?
Yeah.
That's what we're
What is
hoping
that?
for.
We believe that
What's the basis of that belief?
because in the formulation for calculating rise and the final physical size of a foam product uses gravitational force of Earth in the calculation. So we're removing that constant from the equation. That changes everything at a fundamental level. So it affects everything from the amount the foam rises, cell structure, density, who knows what else, really. That was part of what really sparked our curiosity for the idea was this could react completely differently, and it could be even more viable in space than here on Earth.
So how are you designing your tube within which the two chemicals
Very interesting.
connect to account for an uncertain expansion?
We have a small bench test here that we tried to put
So-
together for you guys.
As stated for our scientific process, we have a 3-part chamber here. We have iso on one end, poly in the middle, and we left the third chamber empty to account for expansion and off-gassing. In addition, due to the small volumes and to increase the mixing ratio and get a good consistency, we introduced 2 ball bearings in here to help with agitation. And this has all worked successfully so far on the bench. We ended with this.
So we've proved it works at least here.
Yes.
It would be also interesting from our perspective to see, in the ISS, you're still in a contained environment that mimics an atmospheric environment. It'd be interesting to see how this reacts differently outside in a zero atmospheric environment as well.
Couldn't agree more.
Cool. Thanks.
Any other questions?
I will actually keep us moving. No more questions. Thank you to the first group. Yeah, excellent job, guys.
Thank you.
While we move on to the second group, you'll notice they had some props. If y'all want to talk to them, they're not going anywhere, so ask them about their experiment. Most of the groups set up around here with their little displays, so please feel free to pick their brain and talk more. I know they worked really hard on this. The second group I'd like to introduce is from Allegheny campus. In this group, I'm going to stop before I get to the Latin words. It's the influence of microgravity on the algorithmic growth of a specific type of slime mold. So you guys from Allegheny, you are up. Ready, set, go. Excuse me, guys.
Thanks everybody for coming today. My name is Jared, and these are my partners, Yassine, Isaac, and Bossum. So, the influence of microgravity on the algorithmic growth of Physarum polycephalum. And that is a mouthful. But the real question is, what is Physarum polycephalum? Not a fungus, plant, animal, and it is actually a single cell eukaryote. But it's a little different than the eukaryotes that are in our body because it is actually, like I said, a single cell, but it has many nuclei within the cell itself. And it's thought to be one of the oldest eukaryotes on Earth. How it moves is through physics propelled computational structures. So the nucleus and the slime itself will stretch out itself towards, and then the membrane will stretch to go forage for different types of food. And it does this in an intelligent manner, even though it has no neurostructure inside of it. As you can see on this right here, this was an experiment done by one of the Tokyo universities. So the slime mold, these white ones are sources of nutrients, and the yellow part is the slime mold. First, the slime mold starts to grow out, foraging for food, as you can see with many different tendrils here. But towards the end over here, it starts to actually optimize the pathway that it is for the food. And it optimizes the best pathway, and like I said, without an actual brain to do that. So it has intelligent decision making, and this decision making can actually also help it solve mazes, optimize like the traveling salesman problem, and discriminate between different nutrient sources. The process of the chemotoxins allows the slime mold to increase its internal pressure, like I was saying before, and actually oscillates back and forth, and that's how it keeps on moving and searching for food. So in this next picture over here, the chemoattractive particles that comes off the nutrient source is what the slime mold actually senses, and it moves towards those. what we hope to see in gravity, or in microgravity, sorry, what we hope to see in microgravity is actually vertical growth. There have been experiments on Earth with a Physarum polycephalum where it's mainly in a 2D area, and we don't see any vertical growth. But we hope with the influence of microgravity, it will at least attempt to go up to the food sources that we have on the ceiling of our tube. We also have food on the ground as well, so if it only goes 2D, it can still reach its nutrients, but what we would like to see is the vertical growth. I'll hand it over to Isaac.
All right, as for the overview of our experiment's design, the first part of our test tube in volume A is going to be filled with 2 milliliters of water. From there, we have a clamp that will be removed to allow the water to move to our cardboard slide here, which will house our dormant Physarum held in by aluminum pins. For volume B, we're going to have a half-cylinder shape filled with a substance called agar, which is a water-based substance that will stimulate the slime mold's growth. Within the agar and on the ceiling of the tube, we will have oat grains equidistantly placed apart from one another to accurately read the slime mold's growth in both 2D and 3D. And finally, we have an ABS rod that will support the agar. As for the in-depth design, we have the cardboard slide that is going to stop the water in volume A from overflowing into the dry part of our experiment. The cardboard will become just hydrated enough so that the dormant Physarum will have its growth stimulated without ruining the rest of the experiment. The same mechanism will be used on the on-Earth demonstration and in the microgravity. We'll be analyzing several target areas in our investigation. The ones you can see in green are the ones that will be embedded in the agar, and these will be used to observe the optimization of the mold's growth on an XY plane, the flat portion of the tube, with the areas in blue being airily suspended. These will be used to look at the optimization in 3D on a Z-plane. For our first analysis modality, we chose surface area coverage. The total surface area of the mold in the target regions is going to be measured and compared. Our investigation hypothesizes that the microgravity sample is going to have a higher area coverage in the 3D optimization zones when compared to the mold grown in standard conditions on Earth. The lack of downward force caused by gravity is going to allow the mold to transduct nuclei towards the vertically suspended oats in attempts to create 3D structures perpendicular to the oats on the ceiling of the tube. See?
All right, so our next analysis modality is going to be nuclei density. So as previously stated, the slime mold is a plasmodium, and within that plasmodium there are thousands of nuclei. These nuclei circulate and they become of a higher pressure, and they cause a higher internal pressure on the areas of the slime mold that are nearing nutrient sources along its periphery. In 2D, of course, and under gravitational conditions, that entire phenomenon is flattened, and the highest pressure areas only form on the periphery of the slime mold. But whenever we put this in microgravity, we believe it will be possible for that same effect and that same consolidation of nuclei to appear in the areas perpendicular to oats that are suspended airily. So as you can see here, we're going to use immunohistochemistry, which are basically fluorochrome antibodies commonly used in biolabs that allow you to highlight the nuclei within a cell. As you can see in our first image here, the fluorochrome hooks is used to highlight the nuclei, and that information can be used to derive a density map on the actual slime mold structure. So we believe that whenever we put this in space, we'll be able to apply the same technology to highlight the nuclei density. And in those 3D target regions, we will be seeing that higher consolidation of nuclei, and that will prove an attempt at 3D optimization when the slime mold is in microgravity. Furthermore, we'll also be looking at the overall morphological adaptations. Because this is an exploratory experiment, we are going to have a constant awareness of unexpected phenomenon, and we plan to dissect the exact structures that the slime mold created to find out any nuanced differences between a 2D growth and a potential 3D growth. So to do this, we're going to be looking at the average height or diameter of the slime mold tubular structures at various points, and especially in those 2D and 3D optimization target zones. We believe in the 3D target zones, those areas correlating to the vertically suspended oats, we'll be seeing a higher diameter, a higher height of those slime mold structures because of that transduction of pressure and internal nuclei. So we're also going to be looking at the total number of junctions and the total number of tubular structures to see if the optimization of the slime mold just changed as a result of microgravity. So for the impacts of this, why is this important? Well, the slime mold is a great example of proto-intelligence. As Jared previously stated, this is one of the oldest forms of cellular intelligence or structured cellular beings on planet Earth itself. The first slime mold spawned about 600 million to a billion years ago. And as also previously stated, they're able to derive complex solutions to some very hard computer science and mathematical problems. So we believe that if we can gain a better understanding of the exact limitations of this organism under various physical circumstances, we might get a better understanding of where exactly different evolutionary intelligent characteristics spawned in like an evolutionary timeline of eukaryotes. No, it's a mouthful. Furthermore, we're going to be looking at algorithmic optimization. As previously stated, the slime mold is able to solve traveling salesman's problems, which is where if you have a series of nodes, you have to basically find the most efficient pathway in between all of them. This is applicable in 2D, and it's been applied to many different computer science algorithms and other things to optimize networks and maybe file paths and other things in this field. So some researchers from the Chinese Wenxia Institute have actually modeled a 3D slime mold algorithm, but they have not done the experiment. They have not seen the actual slime mold in a three-dimensional space. We believe that if we put this slime mold in a 3D, in a microgravity space, and we can stimulate that 3D growth, it may be possible to derive valuable information that can inspire further algorithms to optimize, neural networks or other non-Euclidean structures. So I just want to give a big thank you to all the coordinators and directors of the SSEP project and the Keystone Space Collaborative. This has been an honor, and we've all had such a great time, and this experience has been really great. Thank you so much.
So, question. Seeing as how it's well understood that on Earth you're not going to have a 3D structure, what's your where do you plan to do the, gather the data to analyze? Or do you expect the sample to survive the return to Earth and maintain 3D structure?
So yeah, it will survive, but once the slime mold runs out of food or water, it actually goes into a dormant state. And we have some slime mold here. It's not currently still growing, but like we said, it goes into that dormant state. And then once we get it back to Earth, we can, measure, like we were saying, the density, how much it covers, and then we can also put that fluorochrome on top of it so we can see the nuclei density. So we can actually see the nuclei density without it actually being alive.
Yeah. So even if there is even if there's a 3D structure and that structure does fail, once it comes back into gravitational conditions, the high nuclei density will still be available to view in the dormant slime mold. And some studies that we've looked at have shown that mobile and immobile plasmodiums of Physarum share the same nuclei gradient on the target regions.
Question, what's the distance from the slime mold to the food source, and how did you determine what might be optimum for your experiment?
So we did grow some slime mold on 2D surfaces like this, and it can actually go pretty far, but from what we've looked at so far, the oat piece will definitely be close enough that it will reach out to that. Like I said, the slime mold can go pretty far without food, so we feel that it is going to be close enough through the experiments that we've seen so far.
Yeah, we also have done some research that shows that the average creep speed is about, I believe, 4 millimeters per hour. So with that timeline and the size of our tube, and we have, I believe the distance between the tubes, we have it listed here in analysis. It's about 1 centimeter between each oat. So based off that research, we can conclude that the slime mold will effectively cover the entire stretch and return back to its dormant state within the timeline of this experiment.
All right, let's keep things moving. Thank you so much, guys. Disgusting sounding topic, but really cool experiment, right? Slime mold. Super job. A little bit of a different direction, though. Our third group is from our South Campus in West Mifflin. Our third group is going to be looking at the influence of microgravity on the biodegradation of a 3D printed PLA model. So, group from South Campus, you guys are up. Good luck, guys. Excuse me. Get out your mic.
No clicker.
Perfect. Good evening, everybody. As stated before, we are going to be doing an experiment on the influence of microgravity on the biodegradation of a 3D printed algae-infused PLA model. So to start with, what is 3D printing? 3D printing is an additive manufacturing technique which melts layers of plastic and stacks them on top of each other in order to create an object. This is very important for rapid prototyping, resource-limited areas. 3D printing is important on the International Space Station because there is almost no more resource-limited area than space. If tools break or parts break, they cannot be replaced until the next docking period, which could be months, years, weeks, you have no idea. And if somehow they do get a tool that doesn't work for the situation that has occurred, they just have to wait till the next docking period again, which could be years, months, you don't know. So this right here is actually the 3D printer that they use right now. If something breaks, a tool or a part, you can create it in a matter of hours. Then you could replace it with a metal tool whenever it occurs, or if it's a part, just hold on until you get a replacement. So what happens after you replace these tools? Well, if you get a metal replacement, you don't necessarily want to use a plastic tool forever. Depending on the material that is used, depends on what can be done. You can use something like this over here, which is a filament recycler, which basically you break the print physically and rewind it through. Depending on the material, actually depends on this. PVA is a water-soluble material, just dissolve it. PLA and ABS are biodegradable. These biodegradable materials are actually what we want to focus on, specifically PLA. As you can see here, PLA over a course of 80 days actually breaks down almost entirely. It stands for polylactic acid, which is just a polymer chain, and it's very commonly used in 3D printing. The reason it's entirely biodegradable is because it's entirely made out of biomass. And due to that, it can actually be kept in long-term storage for several years without actually having any problems going through a printing process after the fact. So this is actually how it breaks down. You have your original piece here, say something this size. You actually introduce water to it. It separates those polymer chains and breaks them down, upon which you can actually introduce a microbial cell to break it up into smaller molecules, nitrogen, oxygen, carbon, and other biomass which can be then ingested by the microbe. We're going to go more into it, but I'm going to let Cole take over which specific PLA we decided to use.
Okay, so the PLA that we have decided to use is the Algix Alga PLA. This PLA is a biocomposite PLA which uses algae as its main filler. This algae is collected by the manufacturer from algal blooms. These algal blooms are often caused by improper farming techniques which allow fertilizer to run off into water sources. This can cause these algae to be able to reproduce and grow at extremely high rates, which can use up all the oxygen in the water, killing all of the life that is in these bodies of water. So the manufacturer can grab the algae out of these blooms and put them into the PLA, which then also can degrade once it starts degrading, release nitrogen, which can provide a lot of, can really boost the growth of other microbes, which is important because we will be using the bacteria Serratia mycescens in order to further degrade the PLA a lot faster than it naturally does. The reason we chose this bacteria is because we found this paper from their et al. In the study in 2015, and it looked at 4 different microbes, and Serratia was the one that had the most weight loss of the PLA film over a period of 15 days. And now that we talked about what materials we're going to be using, this is going to be how we're going to set up the mini lab. In volume 3, we're going to put the fixative. This fixative will stop the bacteria from degrading the PLA any further once the experiment is over. And it's going to then return to Earth. In volume 2, there's going to be a nutrient broth and the PLA model. This nutrient broth is going to wake up the bacteria once it's mixed. And then in volume 1, there's going to be the lyophilized Serratia mycescens bacteria, ready to be done. And then I'm going to hand it over to Patrick.
All right. So now we've covered our chosen materials, how they're going to work together, and the parameters of the experiment. We wonder about the outcome. How will microgravity degrade the PLA, and will it be faster or slower? We believe this experiment's biodegradation will benefit from the microgravity for two main reasons. The high surface tension of water will keep it adhered to the PLA while it's in space, allowing for a constant surface exposure. Whereas the ground experiment, the water is going to settle because of gravity. Also, the bacteria will have increased motility in the nutrient broth from the microgravity, benefiting from the algae added nitrogen. It'll allow the enzymes that they produce to cover the PLA more evenly. And on the right is just a picture of water in space. It kind of binds to itself. It floats. It doesn't go anywhere. Pretty wild stuff. When the experiment ends and we receive the When the experiment ends, we receive the mini lab from space, where we determine the amount of change between the ground and space experiment in 3 different ways. The first one's pretty simple. We're going to dry off the PLA and weigh it and compare what's remaining to the weight that it was when we sent it up, both of the ground experiment and the space experiment. Next, we'll test the tensile strength of the remaining PLA, assuming that it hasn't been degraded too much. We have a mass or infrared spectro. That's actually the last one. So the final analysis is going to be done by infrared spectrometry or spectroscopy. There we go. To examine the chemical composition of the liquid around the PLA whenever everything's done, so we can examine the how much of the nutrients broke off, how much polylactic acid is in there, how much nitrogen is in it, anything that it can contribute to the compost that we're going to be, ideally putting it in. So how will this information help on the International Space Station, and what's important about using a biodegradable plastic? The International Space Station was a closed-loop system, meaning that everything is recycled and reused. The air that they breathe and the water they use goes back into a system, cleaned, and then reused. Using a 3D printer allows for light manufacturing processes to happen on the International Space Station, which then enter into this loop of materials. Say the plastic that they're using on the International Space Station is beyond repurposing, as we had mentioned earlier, and that it gets used into, or eventually just needs scrapped. You can't repurpose it. Then we can introduce this manufacturing waste into a bioregenerative food system. It would come in with the inedible waste on the top left there, as all the non-usables go into the bioreactor. Our bioreactor, the microbes that we're using as the Serratia marcescens from earlier, would be part of a growing and compounded, we'll say compost on the International Space Station. Beyond the International Space Station, this helps us collectively on Earth. If the biodegradation of PLA objects can take less time than what we... Whoa. Okay.
Gotta watch the back will get you sometimes. Surprise. You got it?
I think so.
I got you. Right
And slideshow.
over there.
Try to do touchscreen.
Secret.
Nice. Sorry about that. So if the biodegradation of the PLA can be done in less amount of time, it might get people thinking at home, how can they compost their PLA? Say they just have a toothbrush, they're using it, it breaks from whatever, flight. They can just throw it in their compost, move right on. This brings a new means of environmental sustainability to the manufacturing supply chain as a whole on Earth as well. Anything that is produced in PLA can be sustainably disposed of. Any of the waste from these larger companies can then be safely just broken down and thrown into a compost. And finally, moving deeper into space, as what this chart from Douglas from 2021 is very recent. Eventually we have no other options but to commit to the closed loop system. Working on the International Space Station, you are limited by resources. So anything that you bring in, you have to use. It's not going anywhere. This is the same as we start to make settlements on the moon and Mars. We will have to continue to operate off this closed loop system, and anything that we learn from these experiments can contribute to those. Special acknowledgements. I just want, all of us want to say thank you to Patricia and Ann for helping us out over at CCAC. They were really keeping us on track and guiding us through the project, making sure we got everything in together on time. Patricia Thompson and Carlos Taylor, who are not here with us, they are teaching probably. They are helping us with the 3D printed objects itself. Alexander is the chemistry assistant instructor at CCAC. That's on the Boise campus, so he'll be helping us with the IR spectroscopy. And Buzz Baldwin, I kept saying Buzz Baldwin earlier, is helped us by giving us the 3D printer filament that we will be using. It has the algae from Algae Algix.
One quick question, maybe I missed it, but so what's happening is you've got algae and it's eating the tensile bar that you're going to test later on, right?
Yeah.
It's going to degrade in its properties, and I'm wondering how you will know. Will you be able to tell at the end if the effect of microgravity was to make the thing degrade faster, or maybe it made the algae more active, or maybe it grew more algae? Or can you tell those two apart?
Yeah, so the serratia marcescens is what is going to be breaking down the PLA. The algae that's in the PLA kind of contributes nitrogen that helps the bacteria grow. It's just fuel source for them. We didn't bring it up in this, it is in the paper. It also contributes nitrogen to the compost that you would be growing. I know that's just an asterisk to your question. Yeah, go ahead.
The algae is actually the biomass that the PLL is created out of. It is not actually affecting it at all, other than what its base components contribute after it has been eaten by the marcescens.
Okay. Yeah, the algae's dead. It's just biomass.
Gotcha. Thanks.
I have a more of a quick process question. How do you ensure, it sounds like timing on Earth and timing and the experiment on the ISS are going to be critical, right? You need to stop and start at the same time.
As close as possible, yeah.
How do you ensure to make that happen?
Constant communication, make sure that we are on board with the same days and times that they plan on doing any interactions with the mini labs.
Additionally, we do have a solution that will actually stop the bacteria from processing too far. At the end of the experiments, that is actually the last step. It will be poured onto it, kind of stop that bacteria from working, then be sent back to Earth for testing. So that way we know exactly when they open it, exactly when they close it, they will tell us that, and then we can compare it to a similar sample on Earth doing that exact thing.
Fair enough. Great.
Yeah, just in case it degrades too fast, then we can actually stop it earlier, I suppose. That's not a bad thing.
Excellent job, guys. All right, nice work. Yeah, constant communication. As long as the message isn't CCAC, we have a problem. We'll be doing just fine. Our next group are some of our apprentices in the skilled trades. So these groups are from the German American Chamber of Commerce's apprenticeship program. And this group is our polymer technician apprentices. So William, Jacob, Jeff, you guys are up.
All
All right, good night, everyone. Our presentation is going to be on the effects microgravity can have on corrosive substances. This here is Jeffrey Schumer, and this here is Jacob Beckinger. My name is William Beverlin. So, brief little overview. We are going to be sending in a piece of steel with saline water. Now, in space, liquid has a unique way of interacting with the world around it. It doesn't adhere, well, it does adhere due to surface tension. Well, our saline water is going to start corroding. Now in space, as we start branching out, we may start to manufacture. Well, odds are sometime, someday, one or another, we are going to have two substances that shouldn't be mixing, touching each other. It will cause corrosion or break down the bonds. So, we're going to be using our experiment on small scale to see if the acceleration or if the corrosion accelerates or decelerates.
Why it's important is, so here on Earth we fight rust constantly here on Earth. What I believe we could be able to do is figure out a way to either see if it will accelerate or decelerate, as Will said. But as we fight rust here on Earth, there are very many key components in the industrial environment, such as your gearboxes, universal joints, drive shafts, bearings. I can name it all day long. But some of those components are very, very key components in a very industrial environment.
Building off of Jacob, all of us have industrial backgrounds. So we're working on machines every day, real life, and rust is very, very something that can have a big impact on your industrial systems. So that can result in failure of the system, and for those that work in industrial environments, industrial process is very messy, very dirty. So as industrial processes start to migrate into space, things such as rust, different impacts on industrial systems can have a large effect on the efficiency and the sustainability of industrial processes in space. For our isolated system that we're going to use to be able to test this, we're going to have a 3-volume tube. Our first volume, we're going to have about 2 milliliters of saline water or salt water. In our central volume, we're going to have 1018 steel rod with the specifications given here, and we're going to abrade that steel rod as well. By bringing that steel rod, we're going to be able to increase the surface area of that steel rod to be able to promote more surface area for that reaction to occur. And then in our last volume, we're going to have a water absorbent pad. Reason for doing that is after the experiment is conducted, we want to be able to absorb that saline water and stop that reaction from happening any further, so that we're able to analyze it after it comes back out of space.
So, upon arriving at the ISS, our experiment is to have clamp A, which separates the steel rod from the water, removed. The astronauts are then going to shake it, so that way the water can adhere to the steel rod. Then we're going to wait and let the process go on. Then, 2 days before it's supposed to come back down, they are to unclamp clamp B and shake it again. This will allow the absorbent pad to absorb the water.
Our predictions for our experiment. Each of us have very similar kind of predictions, but we have a little bit different reasoning or things that we're going to think that's happened. That's what's nice about this thing, where you don't experiment like this. You may not necessarily know what's going to happen, so it's nice to have a little bit diverse opinions on what do we think is going to happen. So me personally, I think that the rust that occurs on the steel rod is going to occur more quickly. For me, I think that's going to be because here on Earth, you're going to you have that saline water that's going to be stagnant due to gravity. In a microgravity environment, I think that water is going to be able to circulate more and have more time to be able to adhere and circulate to cause that corrosion to happen more quickly.
I slightly differ from him. I believe that we will see more rust over the object, but not as deep. I think that due to the surface tension, it will adhere to the whole rod of steel, not just a tiny piece like down here at Earth, because gravity will pull the water down to a specific part of the steel too.
Jacob?
For my prediction, I believe that, as Jeffrey said, it will rust in a more area, but I feel like it would accelerate quicker in corroding.
And then the other thing to add is to be able to have a sample test of what's going to happen is we're going to have this experiment occur here on Earth to be able to have be able to compare them, see how it's different, how it's the same here on Earth. I just want to thank everybody for your time. Appreciate getting to present this to you guys.
Quick question, what do you expect to see, how are you going to quantify the end result? You use power back, it's got some rust on it, how do you?
So that's what's kind of tough to be able to quantify something like this. So I really don't have a good answer of how exactly we are to quantify it. And there are different things to where you can, cut the bar of steel, for example, and see if there's any penetration, especially with that steel bar being abraded, be able to see how far down into those abrasions maybe that rust may have got.
That's interesting. And if this flies, I'll be very interested to read your report and see if I can lead through.
Anything else?
You mentioned 1018 steel. Why that particular steel? What led you to choose that?
1018 steel, it's a common type of steel we use here. Generally, it's used for pins, just smaller objects. So it seems like something that we would use a lot more of. So it's a common type of steel, and we want basically common ingredients.
Yeah, like he said, it's a very common type of steel used in industrial processes where we come from.
All right, great job, guys. Tell you what, the benefit of having industrial maintenance technicians in class is they fix anything on campus when it breaks. It's wonderful. So thanks, guys. Our next group is a little bit different. So our next group is from the biology department. These guys are going to be talking about how microgravity might reactivate different types of metastatic cancers. So terrifying, but excited to hear what you guys have to say.
Good afternoon, good evening, everybody. My name is Dan. This is Jason. I'm a first semester respiratory care student here at CCAC. It's Jason.
And I'm a biotechnology student, and together with our facilitator, Francis Cartieri, we're going to be presenting on the effects of microgravity on the dormant state of cancer cells. Before we get into the experiment itself, we wanted to provide some background information. So, what are dormant cancer cells? So dormant cancer cells are aptly named. They are cells that have stayed in the same spot or moved away from the original identified cancer, and they are like lions in the grass. So they're hiding, and it's difficult to see, but right here is the lion. And so they're sitting there, and they cannot be identified by most medicines, and typically even the body's immune system. So they run a huge risk of recurring cancer diagnoses. And they can stay in dormant states for years, even decades. So the question is, why are they dangerous? If they're not doing anything, if they're just sitting dormant, why are we so concerned about them? Well, there are alarm clocks that wake them up. There are signals in the body that tell them to begin proliferating. And that's when you have issues. So they can enter bone or other tissues that they weren't previously in. And right now, the signals aren't very well understood. So there are a few things that we think leads to dormant cell proliferation, which is inflammation, beta integrin, which is a protein expressed by a lot of common cancers, and E-cadherin expression, again, another protein expressed by a lot of cancers. So what we want to know is, what effect does microgravity have on the cancer dormancy cycle? What does it do to these signals? And if anything. So the reason we think that it may have an effect on these cycles is that there has been studies that prove that microgravity has an effect on things like wound healing, on body immune responses and things like that. So we have reason to believe that it will also affect this type of cycle. And if we look at inflammation, there have been studies that also prove that microgravity can cause inflammation in living organisms as well. This is you.
So we had our idea in place, we did our background research, and this was probably the most difficult part of the process here. It was finding a cancer cell line that was available and that would survive the conditions of this experiment. So then we stumbled across the African cloud frog. So they're the only amphibian that we were able to find that had a cancer cell line available for purchase and has also been researched. We also wanted to find an organism that was a model organism, something that we can compare relatively to humans. And so we were very fortunate to find the African clawed frog. This is what our mini lab setup is going to look like. So we're going to have 2 experimental groups and a fixative in the middle, and then we're going to have a control group here on Earth. So in volume 1 and 3, we'll have our cancer cell line that we're going to be procuring, and the growth media that was recommended by the vendor. And then volume 2, we're going to have a fixative, an RNA protectant fixative, and we're going to fix one of the volumes while it is up in the space station. Experimental analysis. So some certain things that we're going to look at between the experimental groups and the control groups. We're going to look at things like cell count, structure and size, using microscopy. I can't pronounce that. mRNA expression analysis. We're going to be looking for the known proteins, like Jason mentioned earlier. And then we're also going to be looking to see what the difference is between the experimental group and the control group. And one of the experimental groups is going to be fixed, like I said earlier. And then we're going to see if there's any difference between the one that was fixed in space and the one that came back from space and then was introduced to the Earth, reintroduced back to the Earth conditions. We just think that it's a really important subject that hasn't been researched. It's been very little researched here on Earth, and we just think it's really important for future space travel. It's also something to build upon here on Earth for research and other experiments.
Yeah.
So the two end volumes where you have your cancer cells, are those the same?
Yes, they will be the same.
The only difference is going to be the fixative in the middle will be applied to one side and not the other.
Correct. Yeah. So we wanted to remove the reintroduction to gravity as a variable because we specifically want to know what microgravity is doing. So we can see if a reintroduction does make a change, and that would apply to any astronaut with dormant cancer who comes back, right?
Or it goes up.
Or it goes up. Yeah.
Yeah. I just want to say that I really like this experiment because we're getting into a phase where more and more people are getting the opportunity or the need to go to space.
Yeah.
And as we increase the population going into space, lots of folks may have dormant cancer they're not aware of. And are we putting people at risk just to do their jobs, to go up into space? And are we reactivating something that would never have been seen otherwise?
Exactly. Yeah. In our research, we found that it's estimated for 1.9 million people will be diagnosed with cancer. So with increased space travel, you're likely to have someone with cancer going up there.
I have a question.
Sure.
And this is scary. It's not as scary to me as the smart slime mold that was going to grow when it didn't have a brain.
That's fair.
But what is the idea? What's your theory or hypothesis about why the microgravity will make a difference? Is it because they get better mixed, or what do you think is going to happen?
I
Or might happen?
I can take part of it. So the proteins that are currently have been theorized to be relevant to cancer dormancy or proliferation are mainly due to adhesion from cell to cell. So I think that one is a very big.
And in addition to that, we know that these signals respond to the, I am blanking on the word, microenvironment. So changes to that microenvironment should have an effect on those signals, right? And as I mentioned, we know that microgravity affects other cellular processes, and it can even cause inflammation, which is one of the potential triggers. So,
as a quick follow-up, is there a chance that being in microgravity helps?
Absolutely, yeah. And that's something. So that's why we didn't pinpoint our hypothesis to one or the other. We really want to see what the effect is. Because even no effect is an important response, right? Especially with something that's so little understood.
So to be clear, you're putting dormant cells up there, and then there's no activator except for the gravity environment, or do you actually have an activator?
So we're actually going to be putting active cells up there.
Okay.
And we will be comparing that activity to models here on Earth. So we'll be modeling two groups that exactly resemble the two in the FME or in the mini lab up in the ISS. And then we'll have control models as well that will be cultured based on the vendor specifications. And that will allow us to chart a model of what the growth should look like and what the expression should look like. And then we can compare it and see what microgravity does.
I know. Now we're all thinking, do we really want to go on the next Bezos rocket? I'm not sure. But man, that was really interesting. Our next group is going to move in a little bit of a different direction. So this group is comprised of some of our industrial maintenance technician apprentices, and they actually brought in an experiment based on what they do at work. So they run machines that extrude different types of polymers, and I'm excited to introduce our next group from the VECA company. Guys, you're up.
So I'm Josh Mullins. To my right's David Starr. Beside him is Ben Weckerly. With our experiment, we kind of wanted to relate it to what we do with what we do every day at work, what we deal with. We kind of deal with a lot of compound and water mixture, and once that water mixes with the compound, it makes it all clumpy, so you can't really extrude it. The vinyl's no good. So with our material, go to the next slide. At work, we deal with a lot of polyvinyl chloride powder to make our products. We take the powder, we heat it up, make it soft rubbery plastic. Then whenever it's a soft rubbery plastic, we extrude it into a shape, that the desired shape that whatever company or whatever the customer wants. We extrude it into that shape. We cool it down. We make our pieces out of it. We make windows, make sliding doors. Whenever that water gets mixed in with the powder, that batch becomes useless, and the powder in its normal state is like a sand-like substance. Whenever it makes contact with the water, the powder clumps up together and is no longer in its original form. Next slide. This is what it looks like whenever the powder comes in contact with water. So it's all, it's a clumpy surface, so you can't really extrude it into anything. In this state, we are not able to use it because the water and moisture is held together by the powder.
So our experiment question is, will the compound, when introduced to water, form a clump in the reduced gravity state? And next slide. Oh, wait. Go back. Sorry. And the environment of our experiment is made us wonder if the same circumstances would happen with the reduced gravity. we believe that the surface tension of the water would keep the polyvinyl chloride particles from making full contact with the water, and altogether the water and powder would not mix together as it does in Earth's gravity. Next. So what we propose to do is in volume 1, we're going to put 6 milliliters of water contained in that side of the tube. In volume 2, we're going to put 2 grams of our polyvinyl chloride from our company, probably our most used one. And then in volume 3, we're going to have 2 grams of silica gel. It's kind of like the stuff that you get in packages that says do not eat. And the silica, it'll be used to soak up the excess water. So if there's any water left up before re-entry, we want that to absorb it so so when it does come back down to Earth, the water doesn't just mix together like it would at our company.
So for the first day up there, we're going to have clamp A unclamped, and that will introduce the water with the powder. And then 2 days afterwards, we want to be gently shaken for 10 seconds to try and help introduce the water into the powder and break the surface tension of the water. And then 5 days before coming back to Earth, we'll have clamp B open up, introducing the silica gel to soak up any excess water that's left over. And then 2 days before, we're going to close up both of the clamps, have it sectioned off into 3 different sections that see 3 different results. So what we expect to see in the first one, it would be how it would be on Earth, where the water and the powder mix together and get that clumpy surface. And the second one, that's where I'm expecting to see the powder is alone by itself and it's not mixed together with the water. And then the third one, that's where hopefully all of our excess water will be soaked up in. And with that, hopefully our project will be going to space in 3, 2, 1, liftoff.
Very quick question. What happens when you mix the silica with the PVC powder?
I wouldn't expect anything to be different because the powder doesn't have any moisture in it. It's very dry.
So they would just like coexist when the clamp opens?
Mm-hmm.
Thanks.
Why would the water get absorbed by the silica gel, but not the PVC?
More density?
Well, the silica gel, that is a great question.
I don't know either, so.
I have one way to find out.
One way to find out, yeah.
I have a question. You have the center part, I think, was the one that had the powder in it.
Yes.
Right? When I think about the space station, I think about stuff floating around. Will you be filling that entire area with powder, or will it be half filled, and would that make a difference in how the water might move around it?
Well, the way we have it ratioed out was there was going to be more water than powder.
Mm-hmm.
And with that, in the middle section, it's not going to be completely filled.
So there will be some space for it to spread apart, I guess what you're saying. Okay.
Yeah, we sometimes at work we'll have like compound laying on the floor, and if you just put like a little drop of water, sometimes it doesn't just make a nice clump there. So you got to get the right ratio. If not, it just won't. It'll just be wet. It won't clump up like it wanted to.
Makes sense. Interesting.
Thanks, guys.
Thank you.
All right. Our next group isn't really a group. Our next group is an individual. And I just want to do a little context, right? CCAC, open enrollment institution. Anyone can come to us to learn. Same thing for this project. We didn't make anyone take a science class or put any requirements. Any student who wanted to participate was welcome to. And I'm so excited to announce our next student, Hunter, who's doing an experiment on slime mold. I know we already saw one of those, but Hunter isn't in a science class. Hunter is actually in our SEM 105, our introductory college seminar class. the first thing that students take at CCAC, and Hunter wanted to participate in this and really did a nice job putting something together. So without further ado, Hunter, you are up next.
Goodness. Hello everyone. I'm Hunter Laswell, as introduced. My project is on the effects of microgravity on Physarum polycephalum. I have been mentally antagonized by the realization that I put zero gravity in the slide before starting. The material list. Let's just start off basic. Oats. Accessible, nutritious, and most importantly, shelf-stable. There we go. The second is baking soda, or sodium bicarbonate, if we would like to be pedantic. A leavening agent for baked goods, but unfortunately, I was told that we are not able to make cookies in space with this project. I was told that was unrealistic. So instead, we will be moving towards something that I think everyone will agree is significantly more wholesome than even the best oatmeal cookies. Slime mold. Specifically, Physarum polycephalum. Set over a damp paper towel in order to maintain moisture conditions within the tube. So, why polycephalum? Firstly, it's a relatively well-known slime mold, and it is a very competitive popularity contest to achieve that title. It is also rather well studied. A great deal of studies have been done on polycephalum in the past due to a number of reasons. It's become relatively popular in pop culture recently, and the Zoo of Paris recently opened an exhibit showcasing polycephalum in its natural environment. It's also uniquely intelligent, in a sense. We will get more into that later on, but it is capable of solving mazes, anticipating stimuli, and even map making. I don't know a lot of people that are capable of all three of those things. So, why does it matter? Well, first off, despite its in-depth research behind it, it actually hasn't been studied to the full extent of its abilities. There's still a lot of blank space in what we fully understand about Physarum polycephalum. It's also old, really old. It predates all terrestrial plants and animals, and it's also expected that it might be the first terrestrial life on Earth. And despite its remarkable scientific applications, it has an assortment of other fascinating features, such as the fact that, similarly to other slime mold, it starts off as a single cell and forms with others, creating a single-celled structure that is capable of a great deal more than what most would expect. So, for the experiment itself. So, this experiment is planned to track the movements of the slime mold in microgravity as it navigates the unknown territory of the tube that it is given. A similar experiment will also be done under normal gravity at the same time and under the same conditions in order to function as a control group. After the return to Earth, both experiments will be compared side by side to see what sort of differences in the pathing of the slime mold that has been made depending on its environment. So, for the procedure, each segment of the chamber will contain a different substance. Volume 1 will include the sample of the slime mold, Physarum polycephalum. Volume 2 will include a food source, oats in this case, a favorite among its different methods of consumption. And the third will include some baking soda. 2 grams of baking soda to 0.1 grams of oats. The first day of the experiment will actually begin 3 days into the space trip, so that 3 days in between the start and end of the experiment will be given. On the first day of the experiment, the first chamber will be opened. During this time, the slime mold will progress over to the oats and will work its way towards the center and towards and through the center chamber. Once sufficient growth is established, the second chamber will be opened, allowing the baking soda to pour through and dry the slime mold out. This will be assisted by the astronauts that would gently shake the chamber, not to disturb the slime mold, but to disperse the baking soda. Once the baking soda has fully dried out, the slime mold will then die, but will remain in place for further study. Once it safely returns, the patterns of the slime mold can be analyzed and traces left behind, and conclusions can be noted as such. This is important because if the slime mold is left alive for the descent to Earth, then pathing can be made in regular gravity, potentially disrupting the flow of what was made in zero gravity, minimal gravity. As a small gradual crawl for a sample of Physarum polycephalum, but a giant gradual crawl for slime of all kind, perhaps it's time for the originator of intelligence itself to take part in forwarding our understanding of life on planet Earth. Thank you.
I said a quick question. I liked your ending. So I know you're comparing the movements on Earth and in space. Do you have any sort of predictions or guesses as to what might happen in microgravity?
So I would expect that the way that polycephalum paths its way is through its chemical environment and also vibrations. So I expect that there will be a substantial difference either with how it's see, I wish I hadn't seen the other presentation before this because everything I'm saying sounds like it's ripped off of that. I'd say that a sort of vertical crawl would be likely, considering the along the walls of the cell chamber or of the tube chamber itself. But frankly, I don't know what sort of results would be expected from that.
So I want to say, I seeing all these kinds of judging these things, having a little bit of humor into the thing is actually is great. It's really wonderful. I want to know if you've thought about this part of it. So you have the slime and it's growing to. Oh, actually, I also really like this. Reminds me of Apollo 13 because okay, we need to make this work, this work, this work. Well, we might have some baking soda around, right? If we had to stop slime mold on the space station, so I get that. Question: have you thought about when this slime is starting to grow? If it encounters like a tube that's just jam full of oats, it's got it has to attack those oats that are near it, right? Versus if that was maybe half filled, if it might go beyond that or something. Is that part of your experimental design?
Yes. So what I had in mind was 0.1 grams of oats, which would amount to maybe 5 or 6 oats in the chamber. So it would be very sort of erratically dispersed to give it enough substance to grow towards. But with the way that this type of slime mold paths out, it will actually likely cover the entire interior. It would just be a matter of looking into the patterns that this growth would make.
Excellent job, Hunter.
Thank you.
Thank you so much. All this talk about sending these intelligent slime molds into space, it's like Jurassic Park, right? Just because we can, does that mean we should? We'll see what happens. Our next group is going to move in a little bit of a different direction. And our next group is a good example of why we wanted to make this open to all students at CCAC. So it's a very different type of mold. It's not a slime mold. It's real mold, like mold that infects our food. And our students came up with the notion, we have culinary students, all sorts of programs, we're going to have to eat as we send people into space in more and more quantities. So what does that look like when the food starts to spoil? I don't want to get into it anymore, but I am going to turn things over to our next group.
I'm going, Justin.
Hello, first we'd like to thank CCAC and the GACC for having this and putting this on. It's a great opportunity for every group, and we're all thankful for that, especially that it's in Pittsburgh and we're able to be part of it. So we thought about this for a little bit. We were told about the presentation, and we thought it'd be cool to, one, participate and also come up with something different and to find out the results. So after brainstorming and thinking of everything, we decided to do the mold transfer under microgravity because mold's important to know how it works. So we wanted to know whether or not mold would transfer, how it would transfer up in space. Food's a big important in every day, and if we're going to do more space travel, we won't want to be eating freeze-dried food, and we all know what that looks like, and it's not great. So we want to be able to send actual food someday in the future, and mold's going to be an issue we're going to run into. So looking at all the molds, we decided to go with Aspergillus flavus because it's a very common type of mold in all of your foods. And if you left food in your fridge, you see how gross it is and you get a little bummed. So we want to know how to counter that and how to be ahead of it in the future. So why we did Aspergillus flavus is one, because it's a very good food, very good mold that we run into here on Earth. Also another reason is we looked at it is not very prevalent to transfer in the cold. So with the refrigerator system that we're offered, we can get the food there and keep it with a common. And then in space, we can have it at, I believe it's 75 degrees, so we'll be able to have an actual normal spread. And then once it's done, we'll be able to get our things. Okay.
So here's a diagram of basically the toxicology of flavus. So here you can see we have our mold, and then we have food, crops, and basically in the, sorry, so basically whatever grains or livestock that come into contact with it that people eat, it can cause a lot of different kind of diseases, and that's generally not good. So with our experiment, we're hoping that we can try and find ways to avoid the mold forming in the space and microgravity, and basically just kind of help us get a better thought of it. So here is our experimental method. So we are going to have 3 tubes, one of which will hold white bread, another will hold hard cheese, and the last will hold steak. So we will have 2 volumes, that is volume 1, and then in our another volume we will have the white bread that's contaminated with the flavus, the hard cheese, and the steak.
Okay, thank you. So next here we have our proposed, wait, was it wrong side? Okay, here we have our handling procedure here for the transportation. And we're going to just start it out. We're going to have our test tubes with the cheese, the bread, and the steak. And we chose all solids to go in the tubes. And we are going to ship it from CCAC to NanoRacks in Houston. And then from NanoRacks, that will go to NASA. And that whole process, our test tubes will be refrigerated because the Aspergillus flavus grows at a much slower pace in a refrigerated environment. And on the ISS, I believe it's going to be around, somewhere from like 68 to 70 degrees, and a mold grows at, a much faster rate in a more of a comfortable human living condition environment. So about 60 to 80 degrees is your kind of ideal range for mold growth. And then, so while it's on board of the ISS, we're going to have it there for a couple of days and see how the mold grows in that temperature. And then they're going to ship it right back, or well, not ship it obviously, but kind of fly it down on a rocket ship to NanoRacks. And it will be refrigerated there, and then it'll be returned back to CCAC so we can see and examine the results. And then right here we have our proposed timeline of crew interaction. So this is the procedures that the astronauts will be taking here. And as you can see, it's quite simple, nothing too complicated here. We're just going to have our 3 test tubes, and we're going to have the astronauts unclamp and shake the mold gently for about 10 seconds, and we're going to see how the mold spores and the flavus will transfer over to each, because we have our contaminated cheese and then our regular non-contaminated cheese, and then same goes for the bread and the meat. So just see how that mold transfers, how it grows in a zero gravity environment. So pretty exciting there. Peter?
So this is how our study kind of ties into actual issues on the ISS, particularly with waste processing. In our case, waste reduction. So using Flavus as a model organism as it is on Earth on the ISS, we believe that we could develop a form of food preservation system, a novel food preservation system on the ISS. This obviously has, in addition to waste reduction, this also has the benefit of reducing the cost of shipping consumables into orbit, on separate missions. One such process, actually, this is pretty interesting. It's from a group at MIT. They developed a method of a process of fermentation in a zero gravity environment, and using Flavus as a model in a microgravity setting, we believe we can develop systems such as this in the future. Any questions?
I have a quick question. What is your hypothesis on the behavior of the aspergillus in the zero gravity environment versus Earth? And why? Like, well, how do you think it's going to behave? Differently, same, accelerated, and why?
We think it may behave similarly as it is on Earth on the ISS. We believe, if anything, maybe perhaps that microgravity climates will remove previous hindrances in an otherwise gravitational setting.
So you can see that being an accelerated function?
Possibly.
Yes. I have a question. In the same chamber you chose to put, was it bread, cheese, and meat, right? Why did you choose to have more than one food source? And is there an issue, or how will you, is the mold from the bread going to get on the meat, for example? Is that important?
What we're dealing with are solids, and bread is a grain base, cheese is a dairy base, meat is protein.
Well, basically just give us a variety to see how the mold interacts with different kinds of foods.
Okay.
So we'll have 3 different containers. One will hold the cheese, another the meat, and the other the bread.
Right, so they will all be
explain that.
separated. Yeah.
Yeah,
So
so they
the,
will all be
the
separated
test
from each
tubes,
other.
the cheese and the uncontaminated cheese, and the clamp right in between them. So when they release the clamp, then we'll see individually how the mold spores will interact with all of the our dairy, our protein, and our grain. So awesome.
No, thank you.
Thank you. Thank you guys so much.
Yeah.
Great. Thanks, guys. Just one tip: when the experiment comes back and these nice students offer you some food, don't eat it, right? It could be the experiment. Hey, we're getting down to our last 4 groups, so thank you all so much for hanging in there. The next group is also part of our apprenticeship program. And these guys are going to look at some of the effects on a common building material. Maybe we build structures on the moon one day, looking at concrete in space. Our 2 presenters, we're so excited for you guys.
We're all coming up.
You're all coming up. This is great. We had a little discussion. There's a little fear of presenting, but they conquered it, and they're going to do a great job. Come on, guys, you're up.
Hello. Our experiment involves the effects microgravity has on the setting of concrete. So basically our plan is we would like to figure out, it has been done before that concrete sets in space. We do know this, it has been proven before. What we want to know is, is this microgravity concrete as strong as our gravity concrete? So,
Concrete's first use, the Egyptians developed a substance closely resembling modern concrete by using lime and gypsy as binders. Lime, derived from limestone, chalk, or oyster shells, continued to be the primary pozzolanic or cement forming agent until the early 1800s.
hello, please. Thank you. So concrete is fairly simple in its element. It involves cement, sand, gravel, and water. And here's a more specific graph about the different ratio, give or take. All right, you ready?
Yeah, cool. That's cool. All right, how Earth affects concrete. Here on Earth, the strength of concrete is affected by the environmental factors, especially temperature and moisture. Temperature variation can accelerate deterioration process in concrete. So, pretty much what that means is temperature affects how it sets, essentially.
So the question we're addressing in our experiment, again, is the effect of how microgravity can affect the bonds formed when concrete is mixed in space. So obviously, without gravity, it can't pour correctly. So our experiment, in a nutshell, is we are going to have the three sections of our tube. We are going to have our cement mix in the one section, water in the other, and empty space in the middle. Now, whenever the experiment gets to space, all the astronauts have to do is unclip it, give it a shake, and it'll be good to go. Oh, that says exactly what I just said. Is there any questions?
So what kind of testing are you going to do? Because you're going to do one on Earth and one in space, so how are you going to compare the strengths?
Probably a hydraulic press. Now, my prediction personally is whenever it gets mixed up in space, it's just going to go all over the walls of the tube. So we'll likely have to cut the tube off once it gets back home, and we'll have to do that for the other one too. And I personally think that the one from space is going to have lots more bubbles in it because it doesn't pour, it doesn't set right. If there's no gravity to bring it to one side of the tube or the other, it's just going to be everywhere. So I believe that it's going to be weaker than Earth's concrete.
More brittle.
Yes, more brittle.
So I love this project. I work here at Astrobotic. I'm working on a project right now to make bricks out of regolith on the moon.
Okay.
And we have the exact same problems where we're trying to figure out, we have some bricks in the back that we've made up, and we're testing them to see how strong they are and how the bubbles are and things. So you guys are right. I mean, this is the forefront. This is what we're doing.
That's awesome.
As you when you mix up concrete, I don't know a ton about it, but I know you have to keep it wet to keep it strong.
Yes. Yes.
And so, how do you think in this tube environment, how do you know that you'll have enough water in there to keep it to cure and get the maximum strength? You know what I'm saying? Have you thought about that?
We're probably going to have to do a on-Earth run beforehand to get the ratios right.
Mm-hmm. Yep. Yes.
There's a professor at Penn State, Alexandra Rudlinska, that studies concrete in space, and she's close by. You guys might want to reach out to her at some point before you,
Absolutely.
as this continues,
Yeah.
to see what she studied.
Yeah, absolutely. That'd be awesome.
That's really neat. I hope this flies.
Yeah, we do.
All right, guys, great job. Thank you.
Thank you.
Thank you. Thank you, guys.
Hey, we will take you up on that. If y'all want to share some regolith, we'd love to use some at school, see what happens. Yeah, exactly. Little sharp kitty litter. Hey, our next group, this one's going to be a little bit different. So this one is a group that when I saw their presentation, I learned something for sure. I always thought probiotics were just something I took to stay regular. Now that I'm getting older, this group is going to show us there's a lot more to them, especially when they go into space. So growth of combined phytobiotics and probiotics, you guys are up.
Is it all right if I scoot this microphone?
I just wanted to move it a little closer to the podium. Is that cool?
So, thank you, Trevor. Good evening, everyone. So today I'm going to show you guys about our experiment. First of all, let us introduce ourselves. My name is Wendy. This is Max, Juno, and Trevor. And yes, so today I will discuss about our experiment, which is the growth of probiotic and phytobiotics in microgravity. So what will we cover today? We will cover our purpose. What did we choose this experiment? And what are the experiment methods we are using? And the expected results? And why is it even important to us? So, our purpose. We, in past investigations of microgravity, many research shown that the gut is weaker in space. And that is because the tight junction formation is delayed in space in microgravity, and the epithelial cells is weakened, and it increases permeability of the gut, which cause the bacteria to infiltrate, unwanted bacteria to infiltrate the body, like Salmonella, a common foodborne bacteria. And because of that, we are choosing Bacillus subtilis as our chosen probiotics, which is included in yogurt, kimchi, cheese, buttermilk, etc. It is chosen for its various benefits, which it has it is a aerobic non-gram positive bacterium. It is known to produce significant amounts of enzymes, secretory proteins, antimicrobial compounds, and the most important, it can reduce the inflammatory problems with astronauts when they getting those epithelial cells weakened. And furthermore, we will choose black elderberry as a phytobiotics, which is a herb-derived extract, which acts as a food source to Bacillus subtilis. It has high content of polyphenols, which commonly a food source for probiotics. And they also has a benefit to reduce the inflammatory problems in human guts too. And I will transfer back next to Max to speak about the experiment.
Thank you. As sort of a preface to our experiment, very little of us have had any experience with microbiology, especially in a lab setting. So with the assistance of our wonderful professors, we learned how to use all the equipment and how it's applicable to our experiment. The materials that we have used and will use are listed on this slide. We had to do a form of a preemptive experiment for our background research. We needed to understand what concentration of black elderberry extract would induce the most microbial growth. So we designed a preemptive experiment surrounding that question, and the photos on this slide and the next show our process in doing so. Figure 1 shows the type of black elderberry extract that we utilized for our experiment. Figure 2 shows the varying dilutions of the extract that we produced, and they were all within a solution of distilled water. Figure 3 shows how we pipetted the different solutions into varying petri dishes, and 4, we used a spreader to evenly distribute the solution throughout the petri dish, and we let that sit for a while so that we could make sure that the reaction would take place as we intended so. Figure 5, we displays our inoculation method, A double Z horizontally and vertically. for how we introduced the bacteria to our petri dishes. They then were incubated for 48 hours at 37 degrees Celsius, and figure 6 shows our results from that incubation period. We observed the plates to ensure that the bacteria 1% solution of our black elderberry extract induced the best growth. For our actual experimental design, the diagram on the top left shows how our proposed experiment on the International Space Station would play out in the microgravity mini lab. Volume 1 will contain our freeze-dried Bacillus subtilis in a microquick culture. Volume 2 will consist of a rehydration and growth medium nutrient. Volume 3 will consist of our 1% black elderberry extract within distilled water. Volume 1 will be first introduced into Volume 2 to reactivate the Bacillus subtilis, and following the reintroduction, the bacteria will be exposed to Volume 3 for the experiment to begin proper. Following the experiment and observation of our results back on Earth, we will measure the bacterial growth using a spectrophotometer shown in the bottom figure. We will take the sample and place it in a glass container and pass a beam of light through it to determine the contents. This will allow us to determine both the viable, deceased, and living bacteria within the sample. These measures will then be compared to 2 additional experiments that will take place on Earth. The first experiment will otherwise be identical to the one occurring on the International Space Station, barring Earth's gravity. The second will be a control experiment without the black elderberry extract to ensure the validity of our results. The same method, using a spectrophotometer to measure the bacterial content, will be used in these additional experiments. And now I pass it on to Juno for our expected results.
Thank you, Max. We're going to start with expected results. That's a picture of Wendy and Trevor in the lab. Our expected results is to see that growth would increase when combined with the phytobiotic, which is the black elderberry, and the probiotic, which is Bacillus subtilis. And our second expected result is to enhance the health of the intestinal epithelial cells by combining probiotic and phytobiotic. Sorry, I'm a little nervous. Phytobiotic, which is the black elderberry extract. And now we're going to talk about our goals. Our goals is to improve astronauts' health by promoting a healthy diet, and to observe if Bacillus subtilis can be used alongside current meal plans for long-term health. And also we think for preventative measures regarding common illnesses in space. So illnesses that affect the digestive tract, we feel that this could potentially lead way to help cure some of those common illnesses. And now I'd like to pass it to my awesome colleague, Trevor.
Thank you very much.
You're welcome.
All right. Well, we're very polite in the science club. Press the wrong button. There we go. So why does any of this matter? Well, we want to have a better understanding of health demands from space travel. If we discover that Bacillus subtilis has diminished growth in microgravity, then we know that the astronauts will need some sort of a nutritional supplement, a probiotic supplement. Which brings me to my next point, the health benefits of Bacillus subtilis. Bacillus subtilis is a strong anti-inflammatory, which will help to protect the lining of the intestines, which will prevent a lot of kind of chronic intestinal inflammation issues and that kind of thing. Regarding the black elderberry growth medium, we have a control without the black elderberry, I keep saying blackberry, growth extract, and we want to find out if that will accelerate growth, of course, on Earth, but as well as in microgravity. So for our long-term goals, we'd like to discover whether or not this can be expanded into general use. If we find that black elderberry accelerates the growth, we can expand that into industrial use and then perhaps put it on the shelves. And additionally, black elderberry should increase shelf life of this particular probiotic. And I think that concludes our presentation. Here's our references. And thank you very much for your time and attention.
What is your hypothesis when it comes to actually performing the experiment on the space station compared to the ground?
So
I think you have 3 experiments, correct?
Right.
Space station, ground, and then ground control.
Correct. So that's the fun thing about using bacteria in the body, is that there seems to be according to our research, it's not really predictable, right? We don't know whether or not it will have diminished growth or increased growth. For example, oral plaque has increased growth in microgravity, and other kinds of bacteria have diminished growth. So that's what we hope to find out.
Quick question for you, and this is a question for anyone who's doing these experiments, but your slide triggered it. You know, bacteria will react differently under different lighting environments and sort of external environments in which it grows. What are you doing to ensure that your Earth experiment mimics as a twin to what's being done in the ISS for the external environmental functions that are not within your tube, like light, temperature, etc.?
Right. That's actually a really good question. Max, do you have anything to add about that?
In terms of environment, the ground control and the ground experiment will be done in the exact same microlab tubes, so the environment will be the same. We also know the type of lighting that is used on the International Space Station, so we can ensure that that same type of, whether it be incandescent or LED, will be provided to the exact conditions that they are. For temperature, we have rough estimates from what we understand about the International Space Station, and we'll try to keep that as consistent as possible.
That's great. Thanks.
Nice job, guys. Thank you.
All right.
All right, and now for a reference that no students today understand because it's older. I remember Rocky and Bullwinkle, and now for something completely different, right? Our next group is just something that I did not expect getting into this. So the next group is from our Communication Arts program at CCAC, and they're going to be talking to us about a topic that never crossed my mind, which is how we look at dyslexia in a microgravity environment. So you guys are up.
Alrighty, we just wanted to take a quick thank you for everyone who worked hard on this. Really, your hard work did not go unnoticed. We want to thank you for that. We want to thank our judges for being here. Very nice of you guys to take time out of your days for that. Saying that, let's get into the experiment. Our experiment is dyslexia in a microgravity environment. My name is Mark Huber. I'm a freshman at CCAC North.
My name is Emily Washner. I'm a freshman at CCAC North.
Hey everyone, my name is Giovanna Toledo and I'm in my first semester at CCAC.
I'm Luke Krukowski and this is my first semester at CCAC.
And I'm Avery Wildy, and this is my second semester at CCAC. Okay. So what is dyslexia? Dyslexia is most commonly known as something that people will mix up their B's and D's, but it is not just about that. It's also about phonics, reading fluency, comprehension, spelling, and sometimes even the way we understand numbers. So when determining dyslexia, children are presented with different words, and they're presented in different ways. So they'll be pulled apart and they have to try and say the words, and if they have dyslexia, they'll definitely struggle with that, along with switching different letters within the word. So if you take the word space, but instead of an A and there's an I, it would be very difficult to pronounce. And then also nonsense words or imaginary words. So a made-up word that doesn't actually mean anything would be hard for someone with dyslexia to read and understand.
Okay, so imagine future Martian colonies children. These children we think are going to be different than us. Similar to how astronauts expand in space, their body grows, we think that their bone structure will be different because of the microgravity. We think this will cause effects in the mouth and ears, which will affect sounding out words along with hearing, which could cause different misdiagnosis and dyslexia. Now, if not caught soon, this can greatly harm their people in their future lives. We had a person who was 60 that had dyslexia that we tested, and he got no help when he was younger, so he obviously still has it now, and it's greatly troubling in his business life. This is obviously showing the long-term effects of not catching it soon, and this can affect the future of the Martian colonies greatly. This leads us to question, if tested for reading fluency, comprehension, and phonological awareness, will it be more likely that a person will be misdiagnosed, dyslexic, and micrograph?
In order to create our experiment, we needed to have two groups to test. One will be a group with people with dyslexia, and another one, of course, the group of our astronauts. And these are the requirements that we had for these two groups. So for people with dyslexia, they must be 18 and older, have dyslexia, and be not familiar with the test that we were doing. For our astronaut groups, they cannot have any learning disabilities to be in our group, not be veteran astronauts, and also not be familiar with the test.
Okay. I'm sorry.
You're fine.
That's your part.
Yeah. In this experiment, we had two parts for our test. The part number one, we were testing phonological awareness with a nonsense card game, which is basically nonsense words that by reading them, you need to figure out which word you're actually saying. So of course, people with dyslexia will struggle with this. And for part B, we tested fluency and comprehension with a Dr. Seuss book, which of course with the different words that we always find in a Dr. Seuss book, we will find people with dyslexia struggling when reading it.
Okay, so for the testing validity of part A, we based it off of the game Incoherent. In the game that I had, there were about 500 cards, and I went through those cards and I picked out cards we're calling common occurrence cards, which are cards that most everyone has heard of. And I made sure to take out any bias cards, like there was one card, Neil Armstrong, and I figured that one would probably be easier for astronauts to get rather than the dyslexic group, so I took out cards like that.
And then for the fluency and comprehension, we retyped this into a Google Doc to take out any pictures, to kind of take out any distractions this may cause. And it also affected going page to page, took out any difficulty going line to line. We also chose the highest grade level book, so there's 4 different grade levels Dr. Seuss writes in. We chose that one to make it a little more difficult. Not a very well-known book. Can you say most people we asked did not really know what that was. If we chose a book like Green Eggs and Ham, obviously you're going to know that a little bit more. And then the comprehension questions, to take out the bias, we created them. They involve questions such as author purpose questions. Why would the author choose this to say? Supporting details and main ideas in the different stanzas.
Okay, for the process of part A, the test subject will be given a timer that they're going to set for 5 minutes. They're going to have 15 seconds for each card, and as they go, they'll make 2 piles. 1 pile for cards they got wrong, and 1 pile for cards they got right. Once the time ends, or all the cards are read, they're going to record their data, and if all cards are read before the timer ends, they'll record what time they were left with.
And then for fluency and comprehension, you're going to have 1 minute to read these. You're going to mark your own mistakes. We think it is better to have a test proctor. However, we know for this test that we're not allowed. We think this because during our dyslexic students' reading, they didn't know that they were making mistakes reading some of these, and it's helpful to have another ear and mark your own mistakes. Once the 1 minute timer is over, you're going to flip over and answer the 5 questions we give you, and then you're going to mark yourself correct or false with the data we got. Okay, this is just showing the 4 different subjects we showed. This is showing the words read per minute, and the average for a normal person should be about 150 to 200 words. So that's kind of showing just how much of a contrast it is between the two. The one for does not qualify, they actually had read the book before, and we didn't know that. And you can see with dyslexic people, they have very good memories, and their words read per minute was 150. So you can see that, just how much that helps these people.
Okay, our predicted results for experiment A, we're predicting that the first test in space will be worse than the one that they take on Earth. We're predicting that they're going to get between 0 and 16 cards correct with a 0 to 85% accuracy. And then the second test we're predicting will be slightly better, but not quite at the same level as the test taken on Earth.
And then for experiment B, we're expecting worse results on that first test in space 2 days after they're shot up. In a study we saw, there was an effect, a correlation between dyslexia and astronauts' weightlessness in their cerebellum with microgravity. So that is what we're talking about here. The weightlessness in their cerebellum is going to affect them and cause a little worse, read a little bit worse, and then stressors. So since this is a first-time astronaut, they're going to be more prone to stress, such as just being shot up into space. That's a pretty big deal, right? So we expect, with those two combined, we expect them to have about 7 to 15% less words correct per minute. And then 2 days before they leave, they're going to be tested again. We believe this will be better because they are more familiar with the weightlessness in their cerebellum, but it's not going to be where they were on Earth. And for that, we expect to have a 3 to 7% decrease in the words correct per minute. And then for the reading comprehension and oral comprehension, we believe that it's going to be the same or better, and we believe it might be better because of them taking their time and decreasing the words read per minute, and that's going to allow them to process those words a little bit longer and give them the extra time to think about this question. How you going? Okay, so these were just our studies we used. The balancing act is what we use the most, and this kind of just goes down in order of what we use the most about that. And the balancing act is the weightlessness in the cerebellum. These are all our references, and thank you guys for listening.
Tell you if your judges are astronauts, you'd be picked because that's the coolest, most fun experiment.
So I want to make sure I understand. So you're flying, astronauts are flying, and you're trying to back out performance differences that these astronauts have from being on the International Space Station and try to see how that might mimic or mask perhaps symptoms of dyslexics at that stage. So you're not launching dyslexics on the experiment?
No. We wouldn't, yeah.
All right, interesting.
Yeah, one of our requirements for the astronauts is that they can't have any learning disabilities prior to or during the test because it would conflict with the data. So, yeah, they can't have dyslexia.
Like diminished cognitive activity or
Not cognitive activity, but the Balancing Act does have research on the weightlessness of the cerebellum and how astronauts who have gone up into space will have what mimics dyslexia for days after. And it does go away, and for veteran astronauts, they will end up not having the effects at all, which is why we decided not to let veteran astronauts do the test, because the weightlessness won't be affected.
I thought it was interesting too that you hypothesized the biggest effects would be initial, and then weeks or months later there would be some improvement instead of.
That's also because of the weightlessness. We thought that if the weightlessness gets better over time, then the results of the test may improve over time rather than diminishing.
Gotcha. I have one more question. I know as part of this program that there's a limited amount of astronaut interaction time that you're allowed to budget for, right? Does that play into, do you have enough time in the different periods of time you get astronauts to be able to read the story and take the test? Did that influence the program you did?
Well, we tried to make it as short as possible just to not take up as much time. So that's kind of why we had those 15-second marks. So
Right.
we don't understand it on to the next, right?
Okay.
The 1 minute time, you just try and get that data quick. We analyze it, and it's not.
Okay. Good.
Great job, guys.
Thank you.
I think they make good use of time unless the astronauts drop the cards, right? And they're flying everywhere. Otherwise, I think it's great. Hey, our last presentation, right? This is the final one for the evening. Then we'll do a little bit of judging. I promised Evan he could go last because he said by the time everyone's done, they're all going to want to hear what I'm talking about. Evan is going to talk about brewing in zero gravity. Evan, you're up.
Hi everyone, I'm Evan. I just want to say thank you to everyone who put this all together today, and especially to Justin, who's been everyone's hype man tonight. I think we've all appreciated it. So, my project, brewing in zero gravity. So, for proposal summary, before I get into anything, I want to give you a behind the science of fermentation. So alcohol fermentation is basically the process in which yeast converts sugar mainly into ethanol alcohol and carbon dioxide with a few other byproducts. So it's an anaerobic process, which means that it only really occurs in the lack of oxygen. So the main goal of this project is to test whether alcohol can properly be fermented in a microgravity environment. To properly test it, we'll use different types of samples to give us a greater variety in our experiment. We'll be using different brews such as mead, beer, and wine, and I'll go more into that later. So, why do we need to brew alcohol in space? It's not just to make space travel more fun. To answer that question, we're going to play a quick game. I want each of you to put up 4 fingers. For each question you answer yes to, I want you to put a finger down. So, have you filled up your car at the gas pump recently? Have you recently used any sort of plastic materials like water bottles, grocery bags, or other plastic houseware? You recently brushed your teeth with toothpaste? Or have you recently used any liquid medicines such as cough syrup? Well, surprise, they all contain ethanol alcohol. It's used in so many consumer and industrial products in today's world, and it can be found in plastics, medicines, fuels, cosmetics, and so many other products that I can't even list. So, since alcohol is used so widely in consumer and industrial products that we kind of rely on it today, and being able to produce it while we traverse space won't just be a commodity, but a necessity as well. So, but you know, using tons and tons of rocket fuel to send a couple gallons of alcohol into space, not very efficient. So in the future, it may be easier to make alcohol in space using water we find off asteroids, moons, or even other planets. And it aids in the belief that we must learn how to properly ferment alcohol in a microgravity environment. So, experiment design. So, for our different types of bases, so we're going to be having a mead, a beer, and a wine. So each of these have a different sort of base. For the mead, we'll have a natural sugar, which is honey. For the beer, we're going to have a grain of barley must, which is basically the unfermented juices. And for lastly, we will have wine, and for that we will have a juice extract, grape juice. So experiment materials, here we will have 3 different containers, each having either mead, beer, or the wine, and we will have the liquids in here with a dry Saccharomyces yeast in the other volume. So, type of yeast. Type of yeast we use will have a very big effect on our final product. So I've chosen a simple and very popular yeast strain, Saccharomyces. It's a strain commonly used for brewing alcoholic beverages today, and it's sought off basically for its many attributes, including hardiness, rapid growth, natural adaptivity, and its love of sugar, which is probably the most important. So these characteristics make it very simple and easy to manipulate, and it's perfect for a brewing experiment. Additionally, to preserve our sample's life cycle, or life while it's journeying to the ISS, we will be using a dry Saccharomyces yeast sample. Airlock situation. So, as discussed before, when alcoholic beverages ferment, they produce copious amounts of carbon dioxide. This buildup of gas must be released to prevent the container from exploding, which probably wouldn't be very good on the ISS. But normal airlocks don't typically work in microgravity, so I've engineered a solution. Sorry, give me a second. Do I? Okay. So, microgravity compatible airlock. So, I've engineered an airlock that will work in a microgravity environment. The main parts are a rubberless, small rubber stopper, a rubber one-way waterless airlock, a small sterile PTFE membrane filter, and a stainless steel wire mesh. So, the wire, basically all the components' purposes. The wire mesh is to take advantage of the lack of gravity. So basically when fluids move in space in the lack of gravity, surface tension becomes a very big driving factor in how it moves. So to take advantage of that, we've implemented a small wire mesh to basically the fluid to attach to. So this will be the buffer between the filter and the liquid. It'll allow CO2 to pass. For the one-way rubber airlock, it'll allow the travel of gases to move in only one direction. So I said before, it's an anaerobic process. You can't have air in it. So this will allow the gases to be vented off while preventing air from coming back in. For the PTFE membrane, these filters allow gas to move through while blocking fluids. It's more or less just added protection. So, experiment handling. So once in orbit, the special airlocks will be put in place, and the capsules will be mixed gently. Basically, on the journey to the ISS and back from the ISS, it will be refrigerated to increase the shelf life and quality of our samples. Measurements. So, after our space brews return from orbit, we will look and measure differences in the formation of yeast sediment after fermentation, clarity of our brews, the alcohol contents of the brews, and the contrast between the different types of brews and the bases. So for this, we will use a refractometer, which is right here, and that will be used to measure the alcohol content. The turpentine right here, this will be used to measure the clarity of our alcohol, and a microscope, right there, will be used to measure and look at abnormalities in the growth of the yeast. So after recording this data, we're going to compare it to the different types of bases and our space brews to each other, look for variances in the fermentation process. Hopefully our brews will be every bit as stellar as we hope will be. Thank you. Questions, right? I forgot.
Are you going to be doing it on ground too?
Yes, I will be mirroring it on Earth as well.
Are you going to have some way to stop the fermentation before it comes back?
So basically, after how many days they'll be used in space, the fermentation should stop completely. It'll use up all the sugar, and the yeast will no longer be able to produce alcohol. And also, once it's on its way back, yeast, it's called cold crashing. It basically stops fermentation where it's at. So hopefully, we were going to refrigerate it on its way back, so that way it'll keep the quality up. Any other?
One more.
Yeah.
Did you consider you're creating alcohol? Is there like the little tubes that you're going to go in, and is there any material compatibility issues that you thought about that? You don't want to dissolve the experiment or something, right?
You mean for like the components of the airlock, or?
Yes. Yeah.
Yeah, I checked all that beforehand. The PTFE membrane filter, it is compatible with ethanol alcohol. I went over, I checked all that right before I basically put this all together. So everything should be compatible.
Just have fun. We use it on a rocket.
Good. All right. Thank you.
Thanks, Evan. Thank you.
All right, we talked about the Russian space program for one day, and they all want to send booze up. Thank you all so much. So here's what's going to happen next. First of all, if you're a student, I understand you're hungry, right? So I don't have the actual solution you're looking for, but there's a gift bag for all of you brown bags in the lobby. The brown bags have a Moonshot Museum patch and a snack in there. So feel free to grab your bag, have a little snack. I'm going to retreat with the judges, and we're going to pick our finalists. Probably take us about 20 minutes. So hang out here, eat your snack. We'll come back and share the results soon. Next step in the SSEP judging process, they'll get a flight review. The actual one experiment from CCAC that's chosen won't be chosen because it's the best. There's a bunch of practical considerations for what they're going to send into space on that mission. So for purposes of thinking about this, those 3 finalists are the winners from our community, and think of them all equally. So we'll announce them in no particular order. Before I announce the winners, I do want to say thank you to all the students. Everyone who came out tonight is a winner. You guys did a fantastic job. You blew away our expectations, and the fact that you all came out on a Thursday night is wonderful. I also want to give a thank you to our faculty mentors. Faculty mentors, please don't leave without getting a white bag, without your work with the students. This never would have happened. I acknowledge all the hours y'all put in, just a little small thank you gift. We couldn't do it without a strong faculty team. So now, without further ado, let me announce our 3 winning finalists, and then we have 2 extra awards after that. So our first finalist, I want to make sure I'm getting the names of everyone right. This is Daniel Roth and Jason Gomez, microgravity's effects on the activation of dormant metastatic cancer cells. Daniel and Jason, congratulations. Come on up. Yep. And we'll get a photo with Dr. Bullock, shaking hands. A small trophy.
This is in front of the light.
Yeah. Yeah, that way.
There.
Standing right there in front of the podium. Okay. Good job. Good job. Thank you. Thank you.
Thank you so much. And winning teams, please stick around afterwards. We're going to do a group photo at the end, so don't run away. Right? I see you running away. Don't run away. Our second finalist from this community is our group from South Campus, the influence of microgravity on the biodegradation of a 3D printed algae-infused PLA model, Cole, Hunter, and Patrick. And our final finalist, this group is the one I'm going to have the most trouble pronouncing, but I will do my best. This is Yassine, Bassem, Isaac, Santiago, Jared, and Yuchi, influence of microgravity on the algorithmic growth of Physarum polycephalum.
Okay, how about sliding down this way, fellas? All right. There we go. How about a little more? A little more this way. Oh, yeah, okay. Thanks, everybody.
All right, we have 2 additional awards to announce. So these awards will not go on to the actual space experiment, but there is a prize, a gift certificate to the Moonshot Museum, and a gift certificate to Amazon by some sponsors who graciously funded the event. There's 2 of these awards. One is the Crowd Favorite Award, which was one that our judges wanted to acknowledge as being a very engaging presentation that they really appreciated and they wanted to encourage further study. Our crowd favorite presentation is our other slime mold experiment, Hunter.
Very nice, thank you.
And our final award goes to Outside the Box Thinking, a group that showed tremendous creativity and had an experimental concept that our judges thought would really be useful for commercial space as we move on to strengthen the ecosystem. That's our group that did the experiment on concrete, our concrete group from VECA. Where are you guys? Concrete, Quinn, come on up. Yeah, you guys did it. The biggest group, the hardest photo to take. That's okay. You're here. Thank you all so much for attending. That's everything. I appreciate everyone coming out and supporting our students. I appreciate our students for the hard work they did. Our sponsors, Moonshot Museum, providing the space for what this is hopefully the first of what becomes an annual tradition. Thank you again, and we look forward to seeing you more as this experiment goes on to the space station next spring. Oh, yes. Faculty, please remember to get your gifts before you leave, and everyone else, thank you. Drive safely. Yes, and we'd like to do a group photo out front of students and faculty.